All right, so you learned about the second derivative test for relative extrema yesterday, but we didn't have a chance to do any problems with it. So I do want to go through a couple of problems with you just to make sure that we have it down. As a reminder, when looking at a graph and just kind of remembering everything about it, if you think about this relative max right here and this relative min right there, at that relative max right here, I'll call it on our number line here, I'll call it critical point 1 and critical point 2. F double prime at that critical point 1 is going to be negative, right? It's concave down here. So at that critical point, if your second derivative is negative, must be concave down, meaning that must be a relative max. Over here, if I were to plug in critical value number 2 into your second derivative, you're going to see that it's positive. Okay, it's concave up. Again, notice what you have there is a relative min. So this is what our second derivative test is all about. So let's go ahead and actually do a problem with this. So example 1, find all relative extrema for f of x equal to x cubed minus 3x plus 2 using the second derivative test for relative extrema. Okay, so when using our second derivative test, you still need to know your critical numbers. You still need to know where do you have horizontal tangent lines. How we do that is we find our first derivative and we set it equal to 0. And if I were to solve this, could do it two ways. I could add the 3 and divide by 3. I could think about it using our zero product property. 3 equal to 0 gives us nothing. X squared minus 1 equal to 0 gives us 2 values. Okay, so what this is telling us is that we have horizontal tangent lines at 1 and -1. Okay, so now what we want to do with those is we want to check concavity. Okay, so finding our second derivative, which is 6x, we want to evaluate at +1 and at -1 to figure out, do we have a relative max or relative min at those x values, okay? So checking -1, f double prime of -1 equals 6 times -1, which is -6. Since our f double prime at -1 is negative, that means our function there is concave down, and at -1, we have a relative maximum. So what we can conclude from this is that you have a relative max at x equals -1 because f prime of -1 equals 0 and f double prime of -1 is negative. And then if I try our other point by doing f double prime of 1, that gives me a positive value, which means at 1 it must be concave up. And you can see that that's going to be a relative minimum. So our conclusion from that would be relative min at x equals 1 because f prime of 1 equals 0, telling us we have a horizontal tangent line there, and f double prime of 1 is positive, and so therefore we know it's concave up, and therefore a relative min. Okay, so that is how we will use our second derivative test to find relative extrema. Last problem, actually a couple problems I'm going to have you do, they're fairly quick, will be, so number 2, oops, I didn't mean to do that. Number 2, let h be a twice differentiable function okay, all that's telling us when you see twice differentiable just means that there is a second derivative, and h of 8 equals 5, h prime of 8 equals 0, and h double prime of 8 equals -4. What is occurring at this point? Okay, what is occurring at the point 8, 5? Okay, so my question to you, is it a relative min? Is it a relative max? Or do we not know enough information? Okay, so this is where you are using your second derivative test. You're kind of forced to use your second derivative test because you don't know what the function is to use your first derivative test. So, but what we do know is that we have this function value 8, 5. The first derivative equals 0. So what is that telling us? That means you must have a horizontal tangent line at that point, 8, 5. And what we have to decide is if it's concave up or concave down at 8, 5. Because our second derivative at 8 is negative, that's telling us that our function there must be concave down, okay? Which makes this a relative max. We know this because h prime of 8 equals 0 and h double prime of 8 is negative. All right, you're going to try one of those on your own. I'll have you pause it and then unpause it to see that you got the correct answer. Okay, so example 3. Let g be a twice differentiable function and let g of 5 equal 1, g prime of 5 equals 0, g double prime of 5 equals 2. What is occurring at that point? So go ahead and pause this and then come back and check your answer and make sure you justify. How do you know this is happening? Okay? So you should get that 5, 1 is a relative minimum. We know this because at 5, the first derivative is 0. That's telling us we have a horizontal tangent line there. And at 5, our second derivative is positive, which is telling us it's concave up. So if we have this critical number where we have our second derivative is positive, which means it's concave up, it's the bottom of that curve, and that's what makes it a relative minimum.